Hi, I'd like to talk with you today about continuity of functions. A critical piece of information about a function is whether it's continuous or not. Does it have holes? Does it jump? Does it oscillate so wildly that we have a hard time characterizing what it's doing and it can't decide to make up its mind? These are all different ways that a function can fail to be continuous. And in particular, today, I want to talk about the continuity of piecewise defined functions. Piecewise defined functions have multiple pieces, and there will be split points between them. In the example on the screen right now, there are 3 pieces of the function and 2 transition points. The transition points are at x equals minus 6 and at x equals minus 2. The individual pieces, the 1, 2, 3 of them, those individual pieces, those are just polynomials. And so each of those pieces is continuous itself. So the only place that discontinuities can happen for this function is at the transition points. What we want to try to do is answer the question, is the function continuous at x equals minus 6 and x equals minus 2? In particular, we're going to focus in this video on x equals minus 2. We could ask the same question about minus 6 and follow the same procedure in order to answer that question. We will know that the function is continuous, so we would know that f is continuous at x equals minus 2 if 3 things are true. The limit as x approaches minus 2 from the left of f of x is equal to the limit as x approaches minus 2 from the right of f of x equals f of minus 2. So we need to check those equalities. So we need to do the 2 one-sided limits from the left and from the right. And we need to check whether the function value agrees there or not. Let's answer the question first of the 2 one-sided limits. Let's compute the 2 one-sided limits of this function at x equals minus 2. So in order to answer this question, let's compute the limit as x approaches minus 2 from the left of f of x. Okay, so if we're to the left of minus 2, that means we're closer to negative infinity, and we're on the 2x squared minus 3x plus 2 branch, because then x is going to be between negative 6 and negative 2. We're just going to the left of negative 2. So this limit is equal to the limit as x approaches negative 2 from the left of 2x squared minus 3x plus 2. Okay, well, that piece is continuous everywhere. So a one-sided limit of that function by itself, we can always just plug it in. And so we can just plug it in and get that this is equal to 2 times negative 2 squared minus 3 times negative 2 plus 2. That's equal to, let's see here, that's equal to 4, so that's equal to 8. This is 6, so 8 plus 6 plus 2 is equal to 16. Okay. On the other hand, we want to investigate the limit as x approaches negative 2 from the right of f of x. And now we need to look up the branch that we're on. Which branch are we on? Well, we're to the right of negative 2, which means that x is bigger than negative 2. So that means that this one-sided limit is equal to the limit as x approaches negative 2 from the right of x squared plus 2x minus 3. And that itself is a continuous function. And so we can just plug it in. And so we're going to get that this is equal to negative 2 squared plus 2 times negative 2 minus 3. Let's do some work here. That's 4 This right here is negative 4, so those cancel. And this is equal to negative 3. So we've now established that the two one-sided limits don't agree. That is to say that the limit as x approaches negative 2 from the left of fx is not equal to the limit as x approaches negative 2 from the right of f of x. Therefore, I use the double bar arrow like that to say therefore, f of x is not continuous at x equals negative 2. Not only that, but I can specify what kind of discontinuity is it. So because each of the two one-sided limits exist, this one-sided limit exists and this one-sided limit exists, that means that the function jumps at that location. Therefore, I know that f of x has a jump discontinuity at negative 2. Cool, so we answered the question. What was the question that we were shooting for? Is the function continuous at x equals negative 2? The answer is no. It has a jump discontinuity there. So that was a really algebraic way of treating this problem, but there are also graphical ways of treating this problem as well. And since I think of myself as a visualizing mathematician, I wanted to spend a little bit of time talking about how to answer this question graphically. So I'm going to summon up a graphing calculator, and I have entered in the functions from this problem into my graphing calculator. I'm using equivalent to the modern TI-84, where it's going to draw the different curves with different colors for me. I really like that. The new TIs are so cool. So the blue one is going to be the left branch. The black one is the middle branch, and the red one is the right branch. If you're colorblind, I apologize. There are ways that you can turn them on and off, or you could just graph a pair at a time. So if I go to so I'm in y equals now. Now I can push the graph button, and it's going to bring up a view into it. So this calculator that I'm using right now has some pretty neat built-in stuff that the handheld TI doesn't. There are some other weaknesses to this one that the TI-84 handheld is strong in. So I chose this one because I think it's the best analog to what you probably have. So we can see that above each x value, there are 3 points. And at any given time, we're only on one of these 3 branches. So what I'd like to do is focus our attention on negative 2, which is somewhere over to the left over there. Let's see if we can zoom out enough. So if I go over to negative 2, I'm somewhere around here. And let's turn off the branch that we don't really need right now. So we don't need the leftmost branch. We don't really need, so let's just go ahead and clear that one so that we can't see it. Okay, so we're just going to study the negative 6 and negative 2 and the negative 2 on branches. So let's go back to graph. So I have my 2, and the question is, do these two parabola, do they match up at negative 2? Well, I think we can readily see that the answer is no. So if you look at my x values, as I go to negative 2, check out my x values. As I go to negative 2, I'm hanging out around there. We can see that the black one, the left branch, is about 16. Cool, that matches what I computed. And the right branch is at about 3, and that matches what I computed. So these don't match up. So there is a jump discontinuity. So we can tell because my two functions don't meet up at negative 2 that the function isn't continuous there. So there are graphical ways that we can answer the question about continuity of a function at a point. And there are algebraic ways. The formal way is to test using one-sided limits. I'm a big fan of graphical stuff, and so if you can build your intuition using a graphing calculator or other software tools, I think it can really help build an understanding of what continuity means. Thank you so much for watching today. Good luck with finding out about the continuity of piecewise defined functions.